Our sun will not die in a supernova, nor will the overwhelming majority of the stars you can see on a clear night. They will end their lives quietly and beautifully, swelling into vast red giants, casting off their outer layers in glowing shells, and leaving behind a slowly cooling ember no larger than the Earth. This is the life story of a star like our own, a story of steady middle age, of grand and violent transformations, and of a graceful, luminous death. And because it is the sun's story too, it is, in the end, a story about the fate of our own world. The stars that live this life are the low and intermediate mass stars, born with somewhere between about 8/10 and 8 times the mass of the sun. They are the great middle class of the cosmos, and they vastly outnumber the rare heavyweights. Stars lighter than about 8/10 of a solar mass burn their fuel so frugally that not one has had time to age appreciably in the whole 13.5 billion years since the Big Bang. Stars, heavier than about 8 solar masses, die in the fury of a supernova. Between those bounds lies the quiet majority, and the sun sits comfortably among them. To follow their lives, astronomers use a single great map, the Hertzsprung-Russell diagram, which plots a star's brightness against its surface temperature. On this map, most stars fall along a single diagonal band called the main sequence, running from hot, brilliant stars at one end to cool, dim ones at the other. A star's entire life can be read as a journey across this map, a long, near-motionless stay on the main sequence, then a great excursion up and to the right into the realm of the giants, a partial return, a second climb, and at last a sharp plunge down into the graveyard of the white dwarfs. For about 9/10 of its life, a star sits on the main sequence, fusing hydrogen into helium in its core, held in perfect balance between two titanic forces, gravity forever trying to crush it inward, and the outward push of its hot, high-pressure gas. What makes this balance so enduring is a natural thermostat. Because the core is an ordinary gas, it regulates itself. If fusion runs a little too hot, the core expands and cools and the burning slows. If it cools, the core contracts and reheats. This gentle feedback is why the main sequence is the longest and steadiest chapter of any star's life. The fusion itself is a marvel of thrift. 4 hydrogen nuclei are welded, through a chain of steps, into a single helium nucleus, releasing about 27 million electron volts of energy each time, yet converting only 0.7% of the mass involved. To shine as it does, the sun must fuse some 600 million tons of hydrogen every second, and it has done so steadily for 4.5 billion years. The length of that chapter depends overwhelmingly on the star's mass, and it does so in a surprising direction. A massive star, for all its extra fuel, is so luminous that it squanders that fuel in only a few million years. A lightweight, red dwarf sips so slowly that it will shine for hundreds of billions of years, long outliving the present universe. The sun, with its 10 billion-year budget, is about halfway through, and it has not been constant even now. The sun today shines some 30% more brightly than it did at its birth, a slow, relentless brightening that will, in the deep future, transform the climates of its planets. The mass dependence is steep, because a star's luminosity climbs roughly as the third or fourth power of its mass, while its fuel supply grows only in proportion. A star twice the sun's mass therefore lasts barely a billion years, and one of 8 solar masses only a few tens of millions, a brief, brilliant candle beside the sun's long, patient burn. The steady age ends when the core hydrogen runs out. Fusion can no longer hold the very center up, for the core is now inert helium, too cool to burn any further. But the fire does not go out, it merely moves. Hydrogen begins to fuse in a thin shell wrapped around the dead helium core, where fresh fuel still remains. This shift to shell burning marks the star's departure from the main sequence, the first great turning point of its life. The inert helium core, however, cannot simply sit there and grow. Once it has swollen to somewhere around 1/10 of the whole star's mass, it can no longer bear the crushing weight of everything above it, and it begins to contract, releasing a flood of gravitational energy as it shrinks. That energy, together with the fierce burning shell around it, drives the star's outer layers to swell enormously. This limit, that an inert core can hold up no more than roughly 1/10 of the star's mass before it must give way, was worked out by Schoenberg and Chandrasekhar in 1942, and it is the trigger for everything that follows. The star crosses what is called the subgiant branch so swiftly, at least in the heavier stars, that we rarely catch one in the act, leaving a conspicuous gap on the maps of star clusters. As the envelope swells, it cools, and a cool gas is an opaque one. Convection reaches down through nearly the whole vast envelope, and the star is forced up an almost vertical path on the map. It brightens by a factor of hundreds, even 1,000, while its surface stays stubbornly cool, a dull red around 3,000 to 4,000 degrees. The star has become a red giant, bloated to tens or hundreds of times its former size, blindingly luminous and cool to the touch of the eye. At its heart lies a strange structure, a tiny, dense, contracting core, a thin and furiously hot burning shell, and an immense, tenuous, glowing envelope. The great ascent stirs the star's depths. As the convective envelope reaches downward, it dredges up material that was cooked by nuclear burning earlier in the star's life, carrying the ashes to the surface. This first dredge-up enriches the visible star in helium and nitrogen while depleting its carbon and lithium. Changes we can read directly in the spectrum of a red giant, one of our cleanest windows into the hidden churning of a stellar interior, and there is a deep regularity here. Because the helium core is now held up by degenerate quantum pressure rather than by heat, stars of quite different masses all climb to the same tip brightness at nearly the same core mass, a little under half a solar mass, which is why the tip of the red giant branch shines with a nearly fixed luminosity and serves astronomers as a standard candle for gauging the distances of other galaxies. Meanwhile, deep inside, the helium core keeps contracting and heating. In a star like the Sun, it is squeezed so ferociously that its electrons enter a strange quantum state called degeneracy, packed so tightly that they resist further compression not by heat but by the Pauli exclusion principle, the rule that forbids them from occupying the same state. The core is now held up by this cold quantum pressure, almost independent of temperature, and that fact is about to produce one of the most dramatic events in the star's life. Before we come to it, consider what all this means for our own world. The Sun will reach the top of the red giant branch at an age of about 12 billion years, blazing at nearly 3,000 times its present brightness and swollen to some 250 times its current size. Reaching out toward the orbit of the Earth, the most careful models accounting for tides and the Sun's own mass loss find that our planet does not escape. The Earth is engulfed and destroyed by the expanding Sun about 500,000 years before it reaches its greatest size. The last chapter of our world is written, quietly, in the life story of an ordinary star. At the very tip of the red giant branch, the degenerate helium core finally reaches 100 million degrees, hot enough at last to fuse helium into carbon. But here the degeneracy springs its trap. Because the core's pressure no longer depends on its temperature, it cannot do what a normal gas would. It cannot expand and cool to steady itself. So when helium ignites, the released heat drives the temperature up, which drives the burning faster, which drives the temperature higher still, a thermonuclear runaway called the helium flash. For a few seconds, the buried core pours out energy at a rate rivaling that of an entire galaxy of stars. And yet from the outside, almost nothing happens. Every bit of that titanic power is swallowed in lifting the core's degeneracy and gently expanding the inner layers. The star's surface barely flickers. The helium flash is not an explosion but a hidden reignition, deep in the dark, that ends with the core expanded, its degeneracy broken and helium at last burning in a calm, self-regulated flame. Only a few % of the core's helium is consumed in the runaway itself, and a train of gradually weaker aftershocks follows over the next million years or so, until the whole core has been lifted out of degeneracy and settles into steady burning. The heavier stars, above about twice the Sun's mass, escape the drama altogether. Their cores grow hot enough to light helium gently before degeneracy ever sets in. With helium now burning steadily in the core and hydrogen still burning in a shell around it, the star settles into a second, quieter middle age. It shrinks a little and its surface warms, sliding back down and to the left on the map onto what is called the horizontal branch, or, for stars of the Sun's rich composition, the red clump. In the ancient, metal-poor globular clusters, these stars spread out along a nearly level line at about 50 times the Sun's brightness, the horizontal branch that gives the phase its name, and some of them, sitting in an unstable zone, pulsate rhythmically as RR Lyrae variables, their steady beat serving astronomers as another yardstick for measuring cosmic distances. But this second piece is far shorter than the first, because helium yields only about 1/10 as much energy per kilogram as hydrogen did. The star burns through its core helium in perhaps 100 million years, 1/10 of its main sequence life. And when the helium too is exhausted, the star is left with an inert core of carbon and oxygen, the ash of helium burning, and the whole drama begins again, one turn further on. Now the star climbs a second giant branch, called the asymptotic giant branch, more luminous and more bloated than it has ever been. It carries two burning shells at once, helium just outside the dead, carbon-oxygen core, and hydrogen farther out, and it swells to among the largest and brightest of all cool stars, many of them pulsing slowly over hundreds of days as their outer layers heave in and out. The defining feature of this late stage is a deep instability. The thin helium shell cannot burn steadily. Instead, it detonates in periodic flashes, thermal pulses, brief runaways lasting only a few hundred years, separated by long, quiet intervals of 10 to 100,000 years in which the hydrogen shell does most of the work. Each pulse stirs the star, and in the calm that follows, the convective envelope can reach down and haul freshly forged carbon up to the surface. Repeated pulse after pulse, this third-dredge-up can raise the surface carbon so high that it overtakes the oxygen, and the star becomes a carbon star, its spectrum smoky with carbon compounds. And here, on the asymptotic giant branch, one of the great cosmic forges of the heavy elements is at work. In the quiet between pulses, a thin pocket of carbon-13 releases neutrons slowly, and those neutrons are captured one at a time by iron seed nuclei, walking them patiently up the periodic table, to strontium to barium to lead. This is the slow neutron-capture process, and it builds roughly half of all the elements heavier than iron. The proof that it happens here and now is beautiful. Astronomers have found technetium in the spectra of these stars, an element with no stable form and a lifetime far shorter than a star's, which means it can only have been made in the star itself, within the last few thousand years. All the while, the star is bleeding itself away into space. Mass loss, a trickle on the main sequence, becomes a flood on the giant branches. In the cool, distended outer atmosphere, grains of dust condense out of the gas, and starlight pushes on that dust and drags the gas along with it, driving a slow, thick wind, moving at only 10 to 30 kilometers a second, out into the dark, at a rate that climbs relentlessly as the star ages. As the star nears its end, that wind accelerates into a ferocious superwind, tearing the entire outer envelope away in a few tens of thousands of years. And it is this superwind, not the running out of fuel, that ends the giant's life. The star simply loses its envelope. A star born like the Sun gives most of its mass back to space, enriched with the carbon, the nitrogen, and the heavy elements it forged and dredged to its surface, keeping only a remnant core of some 6/10 of a solar mass. The most massive of these giants shed as much as 4/5 of everything they were born with. Aging stars like these are the galaxy's chief source of carbon and nitrogen, and half of the elements beyond iron. Their dust drifts out to seed new stars and new worlds. What these dying stars exhale becomes, in time, the stuff of planets and of life. Once the envelope is stripped away, the star's naked core is laid bare, hot, dense, and no longer burning. With no fuel to sustain it, it contracts, and its surface temperature climbs from a few thousand degrees up toward 100,000, and it races across the map toward the blue. The dying star has become the seed of one of the most exquisite objects in the sky. We call it a planetary nebula, and the name is a lovely mistake. When William Herschel and his contemporaries first spied these small, round, greenish disks in their telescopes, they thought they resembled the pale disks of the planets, and the misnomer stuck, though they have nothing whatever to do with planets. A planetary nebula is the glowing shell of gas the star has cast off, set alight when its exposed central core grows hot enough, around 30,000 degrees, to flood the surrounding gas with ultraviolet light, kindling it into a glow that often shines in the ghostly green of ionized oxygen. The shells are shaped by a collision of winds. A fast, thin gale streaming from the hot central star catches up with the slow, dense wind shed earlier and plows it into a bright, expanding shell. Many of these nebulae are strikingly unround, elliptical, hourglass-shaped, or delicately symmetric, and what sculpts them so is a lively question, with a hidden companion star, magnetic fields and rotation all among the suspects. But whatever their shape, they are fleeting. A planetary nebula disperses and fades within a few tens of thousands of years, so that for all their beauty, they are only a brief, glowing breath at the end of a star's long life. At the heart of the fading nebula sits the true remnant, a white dwarf. For a star like the Sun, it is a sphere of carbon and oxygen, holding about 6/10 of the Sun's mass, crushed into a ball no larger than the Earth, so dense that a single teaspoon would weigh a ton. It has no fuel left and cannot hold itself up with heat. Instead, it is supported by that same cold quantum pressure that drove the helium flash, electron degeneracy, the sheer refusal of the electrons to be packed any tighter. Its interior reaches densities of 1,000,000 times that of water, matter compressed beyond anything found on Earth. This quantum support has a strange twist. A more massive white dwarf is not larger but smaller, and there is an absolute ceiling on how much mass one can hold. As the mass grows, the electrons are driven toward the speed of light, their pressure falters, and above about 1 4/10 times the mass of the Sun no white dwarf can stand at. Subramanian Chandrasekhar derived this limit in 1931 from the marriage of relativity and quantum theory. A white dwarf pushed past it, by stealing gas from a companion or by merging with another, ignites its carbon all at once and is annihilated in a type Ia supernova, the very explosions whose dependable brightness lets us measure the size of the universe. But a solitary white dwarf, left to itself, simply cools. With no fire to feed it, it radiates its stored warmth away into the dark across billions of years, dimming and reddening along a path we understand in fine detail. As its interior chills, the ions lock together into a rigid crystal lattice, a vast cosmic diamond, 1,000 kilometers across, releasing a trickle of latent heat that gently slows the fade. Because that cooling is so precisely understood, the coolest and faintest white dwarfs have become clocks, used to measure the ages of star clusters and of our galaxy itself, and they carry a quiet message about the age of everything. The very oldest white dwarfs have been cooling for nearly the entire lifetime of the universe, and not a single one has yet had time to grow completely cold. The final state, a dark, dead cinder called a black dwarf, belongs to an epoch so distant that the cosmos has not yet reached it. So ends the life of a star like the Sun, not in a violent flash but in a long and stately decline, the patient light of the main sequence, the swelling red giant that will one day swallow the Earth, the buried fury of the helium flash, the pulsing forge of the asymptotic giant branch, seeding the galaxy with carbon and the heavy elements, the brief glowing grace of the planetary nebula, and at the last the slow fade of a crystallizing ember into the endless dark. It is the fate that waits for our own Sun, some 7 billion years from now, and the fate in the fullness of time of almost every star in the sky.